Today's talk is by our very own Milan. Milan has been a member of sales since the middle of the fall semester, and he's doing his thesis on adaptive discount factor in reinforcement learning. Milan, the floor is yours.
Thank you. So let me start my presentation. Hello, myself Milan Zinzuvadiya, and I'm from Cell Lab, and I like to present the adaptive discount factor and reinforcement learning topic. So this is my research topic, and I'm doing my research on that. So I hope that at the end of this presentation, everyone is getting a little more excited about reinforcement learning than the before. So let's start. So let me first say about artificial intelligence. Artificial intelligence is a branch of computer science that deals with the intelligent agents, and it has the subdomain machine learning, and machine learning is particularly divided into three paradigms. So first is supervised learning, unsupervised learning, and the third one is the reinforcement learning. So let's introduce what are they and how they use. So first of all, the supervised learning. Supervised learning makes machine learn explicitly. It means that you need to give the machine, or let's say any intelligent agent. In my presentation, whenever I say machine, agent, or uh, machine agent or AGI, it's a synonym. And so let me so when I say machine, it's a computer, and it's an intelligent. I talk about the intelligent machine. So for machine to learn from the supervised learning, it's a in supervised learning we give input and output to train for the training of a model. So in each input has a label for particular output, and from the large number of samples, machine learn the pattern among them, and machine can then identify unseen objects during the training. So let's move on to the second one, which is unsupervised learning. In unsupervised learning, we only give input to the machine, and machines, particularly unsupervised learning, is used in clustering the data. And by clustering I means to categorize and classification. So in that, so we just give the inputs. We don't explicitly tell machine to which output it should prefer. So uh, basically that's why it says unsupervised, because we don't give the output labels during the training of a unsupervised learning algorithm or unsupervised learning process. So at the end, so in the third, and that's what I'm exciting about, and I'm doing research, is about reinforcement learning. And and I'm more excited about reinforcement learning because reinforcement learning is more close how the animals and humans learn the thing of the environments. So unsupervised and supervised learning, we give the data and try to use the estimate and patterns of our the estimate and finding the patterns among the data. But in reinforcement learning, we create a virtual same environment for any intelligent agent to interact with. And by interacting with the environment, the agent learn. And so when I say reinforcement learning it's uh, it's it's learned with the interaction of an environment. So first of all, when the reinforcement learning uh, age any agent interact with the environment, it certainly has some reward, and reward in terms of positive or negative rewards. It performs some actions and record the changes in the environment, and then it store the information about how the environment works, but it didn't have the explicit environment setting beforehand. So that's the way it's more likely towards the human and animal learn, because when we born we don't have this whole world experience. So that's called the experience based learning. So when we have the more and more experience of a world, we gain, and we we become more comfortable with the interaction with the world. And some as the delayed consequences is one of the most important feature of reinforcement learning, and that's what importance when we talk about the discount factor particularly. So in terms of layman term, delayed consequences is when we perform some action, it it didn't it doesn't just affect the current state or the current time. So let's say in a if we do something now, there and maybe the actions affect us in the future, and that's what we call the delayed consequences, because the consequences is not immediate when we do the action. So in reinforcement learning also we we build in such algorithms to when the agent interact with some particular state or particular environment. So that's at that time the agent gain and agent performs some action. It action doesn't have the immediate consequences. So it's concerns about sequential decisions, because if the agent makes sequentially good decision, then it achieve what the agent try to achieve in particular environment. And we set up the environment, so we set up the goal and we set up the terminal of any environment. And one of the challenges of a reinforcement learning is that in any in any environment, um, we cannot create the exact environment as we have in the real world. So that's that's also the kind of thing to is one of the challenges of reinforcement learning. So yeah, so this is a graphical representation of what I just said. The agent is we program the agent to interact with the environment. We create the virtual environment. Same it's the same as if you learn about supervised and unsupervised learning. In supervised and supervised learning, we create algorithm accordingly to the data, according to the task, and that's the same thing here. We according to the task, we create the environment, and then we program agent to interact with the environment. Agent performs some action A, and then environment has some changes or some positive or some negative reward given to the agent. So that's what I mean by the environment and the agent. Let's say if we want to train the dog, not the particular machine, so we throw the stick, and that's the dog learn by when we try to pet them, or just uh, we perform some good actions. We 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 I'm, I'm sorry. We try to pet the dog. We perform some action to train the dog. We give the food for the good action, and if the dog do something wrong, then we we try to um avoid avoid giving the good stuff, or just punish him. That's the negative reward. That's what we call in reinforcement learning term. So I hope everyone is clear about what's the reinforcement learning beside the supervised and unsupervised learning. So before I move on to the fast track of mathematical terms and equations, let's clearly define the terms in reinforcement learning. The first term is agent. It's a learning and acting part in reinforcement learning, which defines certain actions which allowed to interact to the responsive environment. Here, the responsive environment means that when the agent interacts with the environment, agent may be changed or may not be changed by doing the current action. So the state, every scenario which encountered by this agent is called a state. So when when at the beginning of training of an agent, when agents start to explore the environment, it start with the initial state, which is called the initial state or the starting state of an environment, and reach the terminal state. That's what the task to we want to learn, or we want agent to learn the particular task to achieve in a particular environment. So what's the episode? So let's say the agent start with the initial state and reach to the terminal state, but terminal at the ending state, and from starting to the ending state, that's particular one of a traveling, that's called that's called a episode. Episode is particularly one single thing when the agent you start with the initial state, reach the final state, and gain experience and update accordingly. So that's, and because in every other paradigm also, in machine learning, supervised or unsupervised learning, we have the epoch. That's what we call the iteration of same data. So that's when we interact with the environment. That's the most closest term in a reinforcement learning. So what's called the trajectory? So let's say in starting of episode, if agent start from the initial and the reach the terminal state. In between, the path formed by the states which agent transition happen is known as a trajectory. If an episode does not reach a terminal state, sometimes agents doing the wrong actions and doesn't, because agent don't have any knowledge beforehand. So sometimes agents stuck in some actions and make a loop. That's called, then it's an infinite horizon episode, it's called. So, and so I separated two terms specifically, the because that's what I'm interested I'm interested in researching. And the first one is a reward. So reward is a numerical value provided by the environment to agent as a response to agent's action. So whenever agent performs some action, so in terms of computation and the computer power and the reinforcement learning specifically term, we assign the numerical value in terms of positive, negative, or zero. So that's when the agent learn that's the particular action, how much it worth. And so return is a sum of all rewards received by the agent during an episode. So in each episode, agent encounters some state, and in particular states perform some actions and get the reward. But at the end of the episode, we consider, and the term is G. So I will explain it in the next slides. So particularly return G is a total and the sum of rewards received by the agent during an episode. And agent goal is to maximize the return. And so that's the particular goal in a reinforcement learning for agent, to maximize the maximize return. In here, the assumption is that we we assign the positive values for a accomplished task. So if we say that we assign the negative value for the accomplished task, we can say that your agent goal is the minimization of return. So now, before moving towards the particular reinforcement learning stuff, I need to explain the basis of reinforcement learning. So that's based on the Markov decision process, and in Markov state, and Markov defined that if any state is considered to be Markov state, that if the possible future state from that is independent of the past states. So I will give an example to more to give you the more clarity in this what's the Markov decision process and what's the Markov state. So in other words, the same is the state is called Markovian or a Markov state if the next reachable state is only dependent on the current state, not on the previous state. So let me, and in mathematical terms, the Markov decision process MDP is described by a tuple, which has 5 parts: state, which represented as S, A, action, which represented as A, R is the mapping of the transition between the immediate reward, and P represented the transitional probability. So in this way, sometimes what the action perform, we don't have the particular deterministic state, and which I will talk about in the next slide. So P represent the transitional probabilities, and that's what we're interested in is a gamma, which represent the discount factor. So that's the Markov. And now I like to restate and explain what the particular Markov decision process Markovian state I like to explain here. The Markovian state, as as it says, that it does not depend on the previous state, previous all states or the previous history states. We just depend on the current state from the next state. So let's say if certain person has an at point A, and person wants to go point B. So irrespective of where the person were before point A, the shortest path between the point A and point B, or the GPS route between A and B, should be same, because it does not depend the point the person is the person where in 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 any other state, but now the person is into the place A, so that's the route it's followed from A to B. And I hope that everyone understand what's the Markovian state. So now particularly let's talk about the discount factor, that's the main particular interest in this MDP process is discount factor gamma. So as I said, when agent interact with the particular state, the particular state give the immediate reward, that some actions give the immediate reward. But there are some cases when there are some cases when the agent interact with the state, which in current state, the state may gives the zero or the doesn't give any reward at all. And let's say the agent have several options to consider which action to perform or which next state to go. So in that case, sometimes the immediate reward is less, but the following consecutive state has the larger reward. So for consideration of this, we use the discount factor gamma to assign the current valuation of a future state. So that's, and it represented as I said, the when we try to maximize the GT or the and discounted return of a particular state is a sorry discounted return, and RT is particularly the reward at the time step T, because uh, time step is basically when the each state agent transits between the first state and the second state. It's called the once time step. So, and gamma is represent the gamma value, the discount factor gamma is particularly between 0 to 1. So because we want to consider the immediate reward is to be maximum, and then we move on to the next state. So you can say in the equation right here, the GT is equal to RT plus 1. So there's the immediate reward plus the next state immediate to the next. So it's a second state from that reward, and that's called the gamma into the particular immediate reward of that state from an environment. So when we do the gamma square, it decreases because its value is between 0 to 1. So each and every time step, we de-evaluation of state. So in that de-evaluation, each and every I'm sorry. So in the de-evaluation of a future state, because each and every time we need to keep it balanced between the immediate and the future state. So basically the gamma factor represent how much we want to give value to the future state. So, and that's when I like to discuss also the MDP policies, which is policy by specified what action to take in each state. So after the number of episodes, agent find particular optimal policy which is best to reach from the starting state to ending state. And policy can be categorized into two: the deterministic policy and the stochastic policy. So in deterministic policy, so fixed action for each state, and it's already determined. It's I'm sorry. In deterministic policy, if we take certain action, then it is it always results in the same next state or the same state. But in stochastic policy, we introduce with the probability state. So it's not necessary that in each state, any state, sorry, my mistake. In stochastic policy, in any state, if the agent has in any state, then the certain particular action repeatedly doesn't guarantee to to provide the fix the next state. And from that, I like to talk about the Q learning part, and also like to talk about the grid world. So in grid world, so basically here is a square environment, then some boxes to reach from start to end, and there are particularly two end. When there is a positive end, that's when that's what we want to, what the what the what the task is to be achieved to reach the positive start, ending state from the starting state. So you can see in the left, there is environment we create to agent. The agent particularly doesn't have any information about environment, but in each square boxes which represented as a state in the next in the left grid environment, the particular any state is has certain actions. Let's say that each square boxes has 4 actions: up, down, left, and right. So agent can go from start to up, start to right, and agent from going there at the end. When the agent reaches the end, it updates the trajectory, which I just explained. Trajectory is a path from start to the end during the episode by an agent. So particular trajectory will be updated at the end of each episode. And in Q learning, we try to find out the which particular actions in which particular state provide the maximum output in terms of environment. So in the right, when the Q learning is done, the that's what the final value. It's about when the starting state has the maximum value of 0.79, which is the upward direction. So the Q learning is what we try to find out the state and action pair, which has each state has a 4 action. So that's the triangle represent state action pair, and each of the triangle is updated accordingly to the number of episode performed. So if we perform and at the end, maybe the inequality changes, maybe the numbers here are changes, but the state particular state, particular action has the maximum potential to reach the positive end is same. So when at that time we say the grid world is converged. So here you can see at the start the state action for the up down there, the 0.79 is the maximum. So the Q learning said it should go up, and then at the upper state the 0.84 is the maximum. So again the Q learning at the end said it should go upward, and when we reach at the upward, we said 0.88, which suggests that in particular that state and the action pair, so that state and the right pair has the maximum value of 0.88, so it should travel towards right. So that's what the right, and then right, and then right, and we can achieve to 1. We can achieve our positive, and that's what we task set by creating particular environment. I hope everyone is clear about according till now. Okay. So that's different approaches, and that's what let's say we have the agent which uses the deep learning to observe the environment, and taking certain action. So let's say the policy has certain action pair, state action pair. That's, you can see pi theta here into the left side, and that's what the agent, the same diagram we already observed, but with the deep learning, we with leveraging the advantages of deep learning, and that's called deep Q learning, because it's also leverage the advantages of deep learning to, you know, in reinforcement learning. And it's a it's a subfield in a reinforcement learning is a deep reinforcement learning. So I I try to overview that here in this presentation. What's the deep reinforcement learning is. That's this. And now let's talk about why we need the adaptive discount factor. First of all, so Abhishek Naik studies the what's the some study the in the research paper. Abhishek Naik and group stated that because the discounting in reinforcement learning is fundamentally incompatible with the large scale reinforcement learning in more of a continuous task. So let me say what's this uh, what's this meaning, right? Because we use the discount factor to estimate the future state value to the current. So that's the particular exponential, because every time in every state we assign here, let me show you the here the gamma is increased by the factor of gamma, so it's exponential growth of discount factor, and which is traditionally and the most widely used and currently using reinforcement uh, in re, currently using discounting future rewards in reinforcement learning. So the and that the what's the marsh the again the marshmallow experiment is, I guess everybody's familiar with. In that, the small 5 years children give one marshmallow and wait and told them to, if they can wait for half hour, sit in front of um, in front of a table which has the marshmallow without touching it and without eating it, then the children can get the double reward. It's a two marshmallow. And that study, after the same all the children is getting accounted in the study after the uh, after they go to the colleges and they go to the university. It's found that the children who can wait for the greater reward, not accessing the immediate one marshmallow reward, are more successful in terms of career than the kids who reach out the marshmallow. And for improving this exponential discount factor thing, I propose the following objectives and methodologies. So first of all, I like I will experiment on the creation of discount factor gamma, which has the three things: the adaptive gamma with the experience replay, with the Bayesian method, and machine learning to estimate the gamma, which is state dependent. So by saying state dependent is that discount factor should not initially assign particular value from 0 to 1 and getting the constant throughout the whole training, but the discount factor should change according to the value. So by explaining this, I like to give you example that, let's say if anyone has choice between right now $100 and tomorrow $200. So getting $100 now or the tomorrow $200. So in this way, in this scenario, person may confuse that maybe the other party who is offering the money is not it, the offering party will not be there tomorrow. So it's a confusing decision because we need to consideration, we are not sure of a tomorrow's reward because we sure of $100. So at the end we said that if we're not sure from the tomorrow, we can say that tomorrow today is the today one can take the $100. It's a more obvious choice to the more person. Yes.
Just reminding you that you have about 10 minutes left, Milan.
Oh, okay. 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 So yeah. So first of so that's what I'm saying. So immediate reward of $100 and the next day reward of $200. So it's more obvious and more general to get the immediate reward because we are not sure of the future. But the same thing offer with the 20-day reward and 21. Let's say the offering party said after the 20 days I give you $100 and after the 21 days I give you 21 sorry, after the 21 days I'll give you $200. So by that, that's the that's the uncertainty in a both 20 days reward and 21 days. So by that means we like to wait one more day to get a $200. So but the current formulation of a discount factor, which is growth exponentially, and that's the state, each state has the same exponential growth. So it's the same choice as today or the tomorrow because the time difference is one day is same for the 20 day and 21 day and today and tomorrow. So that's where the that's where the arise of the need to adapt the gamma according to the state. So let's so that's what's three method I propose for the for developing and the new discount factor, the adaptive gamma factor. So first one is experience replay, and so experience replay is when the training start in certain number of episode. We don't have any um, I'm sorry. Okay. Hmm. So adaptive gamma with the experience replay. So in experience in I'm sorry. Adaptive gamma with the experience replay in the certain states we collect the data and then we use that data to train the the in the beginning we just store the each state and action pair data, and then that in after a certain number of episodes that data can be used to estimate the new unseen state with more accuracy. And that's what I mean by the experience replay because we first get the experience. And adaptive gamma with the Bayesian method, we use the probability method to get that from the uh, available episodes and available state action data to to more accurately predict the next, how much we should consider the future reward. And the third one is using the machine learning to estimate the discount factor gamma. And after that, let's say if I when we were making the discount factor is one thing and comparing with the other one, so one thing is sure is that we can, if we have, if we, even if we fail, then also we have the certain methods that we should have certain methods to compare with the existing, or the if we success or not, we check for that to compare with the existing method. For the evaluation of a new discount factor gamma, i I plan the breakout game, the Atari breakout game, which I guess everyone is familiar with the little dot and the disk thing to 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 compare the current discount factor gamma with the new created discount factor. And I like to, in any ways, I like to present the matrix comparison between the new methods and the current method. And certain researchers already experiment with the new thing to experiment in a particular way to get the insights how we can address this discounting of a future reward thing in a reinforcement learning. So that's so traditionally it's called hyper exponential, but the Google brain researchers try out in 2019 Google brain researcher develop a research paper to leverage the hyperbolic discounting in reinforcement learning. And in a hyperbolic setting, if you say the two curve here, the hyperbolic and exponential, you can see in certain time delay, it means that the trajectory length, the state from initial to ending state path length, and the time step, it's according to that time step, that's time delay. In the beginning, the curve is almost same for the hyperbolic and exponential, and that's what I exactly observe when I experiment thus and implement the same paper published results to implement the grid world and experiment with this small grid world. And I'm planning to work on a complex environment with this. So in this paper, the researcher proposed this approach that.
Milan, I'm sorry for the interruption. We have about 2 minutes left.
Sure. Yeah. Okay. So in this paper, the researcher has the new way to discount the particular state, and it is that the certain actions. So in each state, we calculate the n number of q value, which is basically in each state with the state action pair value, and then the n number, and then multiply with the k to approximate the particular hyperbolic value of a current state. So after experiment with this thing, my results are that it's computationally expensive, because in traditional Q learning, it we just need to compute the one Q value, and in here, if you want a more accurate hyperbolic value, then we need to increase the n, which means we need to calculate the more Q values of particular state in environment. So it's a memory expensive, because we need to store the not just the current episode environment, because the next episode value is depending on the current episode, which is already updated in in agent perspective. But and we need to store the n q value, and in efficient, because when it comes to shorter trajectory, it's same as the q in exponential function, because exponential and hyperbolic is same as in the beginning. And the one thing is, it's not completely hyperbolic due to the approximation, because it's not going to get to this agent to the every state and then compute the hyperbolic value of a particular state, because in that way that's particularly the brute force, and that's also the very computer that's not the efficient way to do that. And the last thing is, let's say we develop the adaptive discount factor, and which is, so in other words, let's say we develop a method that also that by that method we can, if we can approximate the future unseen state and the weightage of a future unseen state in reinforcement learning. So it's at the first, the reinforcement learning is sequential learning, and it in every reinforcement it will affect the every reinforcement learning algorithm, every reinforcement learning application, because each and every because gamma is an universal in reinforcement learning, and it affects the every field that has sequential decision. Let's say healthcare, it has the drug process is a sequential thing to develop the steps, so we can use the reinforcement learning with the new thing to develop the more advanced drug. We can do the computer systems, so we can advance in a computer systems by database settings, and robotics to compute the next, and the financial analysis, because the stocks, and we can stock market prediction and something where the market goes, and the analysis of unseen. That's what means by the future discounting. Natural language processing, because it's also a sequence of thing, and then that it will improve the natural language processing. And as certain, the artificial intelligence is just a mimicking of real intelligence. By developing or by addressing this discount factor, we get more clear insights into our brain. So in that way, the neuroscience is also affected by this research. And thank you. And now for the QA sessions, and I'm welcome to explain things that maybe, or I'm welcoming your questions to answer. So
Milan, thank you very much for this great presentation. I do have a number of questions, but I first would like to open the floor to any questions from the audience.
Okay,
Bibek
I have a
would like to
question.
go ahead.
Yes. So how far have you gone in your research right now?
sorry.
How far have you gone in your research right now? So what are your results right now?
My particular results are in a, as I said, the hyperbolic thing which I implement and tested, and my next thing is to address the same issue uh, with uh, with the varying length of a trajectory to make the dynamic thing, and that's that's I believe, and I have confidence that it will give the good results.
Well, it's certainly promising. I've been following up with your results, and you're following a promising path. I would like to go back to a more fundamental question. As you mentioned in the broader impact section of your presentation, AI is either inspired or can be inspired by nature, by
Yeah.
natural intelligence and neuroscience. I was wondering if you have any thoughts or insights on how our cognitive systems
Hmm.
implement discounting. How does a human brain discount future rewards? Do you have any thoughts on that, or have you come across any studies on that?
In neuroscience, I'm not, I honestly say that I don't have I don't across the study, but I have some thoughts that I have my thoughts that how it should be to the neuroscience and how we have pursue the uncertain thing. So it's as it says, the world is a unique, and every time it's in terms of speaking of reinforcement learning, we can say that each and every state we encounter is entirely new because we'd never seen it before. So we must find the more appropriate and the most closest ones we already encounter. So we never encounter the same environment, same state twice in our life, but every time we encounter, we we have some experiment and we say thing. Let's say the same example I give, the $100 and 200 one. If I choose that, let's say the today 100 and sorry, if I choose the 21 days after $200, and if the person came and gave me $200 and then he said, I will give you today 100 and tomorrow 200, so I'll change at that time because I have confidence and my trust in that person based on the previous one.
That's a very interesting hypothesis that experience plays a significant role in our natural discounting of future rewards. Um, Other than experience, do you think there could be anything else in play? Are there any parameters? Are there any other factors that could play a role in our discounting?
Yes, I guess because I recently I'm currently reading the master algorithm, which try to break down to the how the brain works and evolution process, because certain things the child has already known, means that certain language can we can speak the faster way, certain language we have the interrupting thing. So I guess in neuroscience, in the brain, that it's what we call is not like we want to develop the fields and sections, reinforcement learning, supervised, unsupervised, but I think that's all going on at once in brain, and that's a very beautiful creation. That's can be, and that's what I believe, that it uses the certain part because we also have the education to address the uncertain uses, because every time we visit the Google and type something and buy something, and the typing is also every time is different, the new advertisement is different, the new thing is come to our way is never come before, but we have a certain preference that that side is delivered faster, that side is not, and for that also, and then some knowledge is also imparted and transferred between the humans as a part of education, and that's what we call the education, and then we form the branches, but it's not branches, it's and I like to state it here in terms of neurosciences. My favorite person, history figure, Leonardo da Vinci, he says everything is connected with everything else, you just need to see it. So that's what I believe, that it's not particularly using one thing but all the thing at once, and then
That's a beautiful notion. That's a
yeah.
beautiful notion, and of course, very much in line with the uh, models of the universe as complex adaptive systems. To not diverge too far, to not stray too far from the original discussion, I wonder if you have any thoughts on what what metrics we may be able to look at to evaluate a discounting mechanism, and not necessarily in reinforcement learning, but in human cognition, let's say, or in general evaluation of future rewards. What makes a mechanism better than the other?
I think at in terms of human, not particular, but in terms of human, the best thing here is time itself, because at the time we make certain decision by assuming, by approximating the reward or the education, anything, but what's the evolution that the particular decision is correct or not is when the time came, and if it's happened what we actually try to achieve by that decision. I guess the time here is evolution itself, because certain things I do for tomorrow, and then I wait for the tomorrow, and when the tomorrow came, the certain things happened because of the today's decision, then it's a positive reward, I guess. I say it's a positive reward, and that's the evaluation I make from my perspective to compare. That's what my decision is wrong, right, what's the discounting is wrong or not.
That's very interesting. So hindsight analysis and looking at what happened in the rear view can definitely provide good insights on how well our mechanism is performing.
Yes.
Can you think of any other factors involved in the evaluation of a discounting mechanism or technique other than how it actually ends up performing? Of course, that's the most important factor. That's the objective. But is there anything else involved in tuning the performance or comparing the performance of different discounting schemes?
Yes, I say not just the and, but let's say I have it says there's a sequential decision, so I need to make the certain decision, but let's say I started one path. That's the problem here, I guess, in current formulation of discount factor, because we started the one path, we go along the path, and in between, in real world, if I started something if I want to do something, I started doing it 1 day, 2 day, or 3 day. Let's say it's a task of 1 month, but after 10 days, if I started at the first days and then it's not going in that direction, I change the direction or I change the way. But I changed the discounting also. Let's say I promised one client to deploy AI model in 1 month, and I by looking at the data that I estimate it's 1 month. I working on 5 days on that, and then I realized before it's end, at the time when I working on it, it's not end, but I realized that it takes 3 months. Or that's the way the discounting here is 30 days discounting. Let's say the future, that's what task is done, but we change continuously our expectation along the way. And here the same discount factor which applied at the beginning of a training, it's remained till the end.
That's another interesting insight, and I really appreciate your input on this. I have one more question before ending my streak of all questions, and it's about your personal experiences with issues in discounting. Have you ever experienced any negative outcomes from your evaluation of future outcomes or future values?
I guess so, yeah. And I get, yes, and that's so you want me to give you example, or you
Or you
want?
can give a hypothetical example that could be common in
Hmm,
our not just civilization but the species.
hmm. Okay. So some negative is sometimes we set the some task and we believe the certain thing is correct at the end, till the end, and then my example is, let's say, uh, if I work hard and then I get A or A plus in particular course, but in that evaluation I consider only myself and my metrics of what's the working hard. And let's say I'm when I move from India to here, uh, my working hard parameters are different from the other. So when I say work hard and the other person says work hard, I'm also work hard, it's a different thing, because we that's not the same as you ask about the metrics. Each, it's a relative metrics, but at the end result depend on the how your metrics is closest to the real ones.
That's interesting. I it it made me think about whether we can decouple our
Hmm.
model of the environment we are operating in from the evaluation or discounting of future value. Do
Uh,
you have any thoughts on that? Is
um,
the discounting dependent on our model of the environment, how the environment operates, what the dynamics of the environment are? Or could discounting be completely disjoint and independent of the dynamics of the environment?
hmm. Can you repeat that? I'm little.
So,
Okay.
in your example,
Hmm.
the problem
Hmm.
rose from an incomplete model of how things unfold
Yes.
over time. It wasn't necessarily just a value or evaluation of
Hmm.
particular states or what can happen in future, but it stemmed also from having an incomplete or incorrect
Hmm.
prediction of how the environment operates, how things around us evolve
Hmm.
over time.
Yes.
Now, this made me think whether discounting is dependent on our model of the universe or the environment, or
Hmm.
can we come up with a good discounting scheme that is totally independent of our model or our understanding of how things change in the
Uh,
environment?
um, as I right now, as I see the field and in my perspective, I think that uh, if we even if we come up with the environmental independent discounting, it's not as good as if we come up with the model dependent discounting, because it's also adapt to the model, because model, that's what we're trying to learn here, and that's what we're trying to discount the next state, and that next state is lies on the model. So I in my perspective, if the both ways are there, then I will go with the model dependent discounting. Sorry, environment dependent discount.
Very well. I think this hypothesis is something that you need to tap into in your research.
Yes.
There are already some results that relate the accuracy of a discounting scheme to the accuracy of the agent's model of the environment. We can look into that later. There are a couple of things that I want to
Hmm.
suggest to the audience and yourself on discounting. There's a book called The Economics of Self-Destructive Choices.
Hmm.
It's an interesting title with interesting essays about how we make decisions that seem to be rational when we make them, but end up being completely destructive or completely damaging. It happens. We know that we make mistakes,
Hmm.
and it would be interesting to read and see how the economists, how the behavioral economists look at this problem and model the decision-making mechanism, including discounting in the context of incorrect decisions or damaging decisions. One example is addiction, right? When you indulge in your addictive behavior, you are discounting the future cost or the future reward incorrectly. If you had a good evaluation of the future rewards, you wouldn't have indulged in your addiction, you wouldn't have gambled, or you wouldn't have taken a drug. So these are things that may be of interest to some of you and you might want to learn more about. Another idea that the general audience can look into is the theory of bounded rationality. It's a relatively recent, I'm going to say relatively, I mean in the past 30 years, not in the AI terms, theory of how rational agents make decisions with incomplete information. And discounting comes into play there quite significantly. Very well. I'm done with my questions. Does anybody have anything else to add to the discussion? Any questions, any thoughts, any comments? Venu?
Professor, hi Milan.
Hi.
So
Hello.
I just wanted to know if there is any regulation that can be posed on the discount factor. So adaptive discount factor, as you have been speaking, so it changes accordingly with the environment, right?
Sorry, I couldn't understand your question. Can you more
So
elaborate it?
so is there any regulation that we can put in for the discount factor? So it is an adaptive discount factor which changes accordingly with the environment.
So you want let me. So last part I didn't hear, but let me repeat the question so I can. So you want to know that if we have any regulation, if any regulations in my mind that how I'm gonna implement the adaptive to the which part of a model, or that's what you want to ask me?
Yeah. So when you're applying for the discount, when you're applying adaptiveness to the discount factor, are you putting any regulations that suppose if you are designing an automatic car or anything that considers a life of any living thing, and presently that the discount factor is 1, so that it never discount, like it never reduces. Suppose if you give the reward as -1,000 or minus
Yeah.
infinity, and
Yeah.
you give the discount as 1, and certain point of time it considers that the adaptive discount considers that discount to be something around 0.004, and that minus infinity comes down to a very significant number for which it can consider that any living thing's life can be less rewarded. So
Yes.
that
Yes.
can be a disaster. So any regulations regarding that?
I guess that when we try to implement the autonomous vehicles or such a thing, when the possible life may be in danger. So in that, I like to answer this in a two part. The first part is at the start of a presentation when I said that the challenge of a reinforcement learning is to create the environment as much possible as close to the current one. So when you say about the child and stuff, so when we try to develop the reinforcement learning for a particular task of autonomous vehicle or such thing, when the life is in danger, we need to consider to train, and that's the reward you said, the minus infinity or plus infinity. But at the end also we need to have the separate, the hard coded, the actual software engineering software which control the model of a reinforcement learning. As you said, let's say some point it says 0.001, but then also we can check in a hard coded way that if there is a life in danger, then don't perform it.
So I want to interject here. I believe that everything that we know and we do as natural instances of intelligence are emergent through an evolutionary process that includes learning. That includes laws and regulations. So laws and regulations can also be the result of a learning process. With regards to Venu's example, like the problem, the negativity of hitting a human pedestrian and causing damage to somebody's health or well-being, that is typically captured in the reward function.
Yes.
But of course, the discounting mechanism should be designed in such a way that it does not diminish beyond a practical threshold the value of a future reward or cost that may be associated with these critical decisions or critical actions. This is a much longer discussion. I actually think that what Venu brought up is a very interesting question, and it should be a guiding principle around what should a good discounting mechanism look like, or what are the properties of a good discounting mechanism, which of course comply with the basic principles of rationality.
Yes.
Milan,
I like to add one thing to Venu. That's when Venu says, let's say minus infinity or plus infinity in the discounting thing. I just like to add that certain, like let's say all the other states has some very low value and one has the infinity value. It damages the learning process itself because it makes the neighboring states of a particular life states also in the long neighboring states in a very negative value. So that's also we need to consider. That's the thing when we consider about the reward. But it's that's the thing I want to tell the Venu.
Very well. So let us conclude this session. We are slightly over time. Milan, I would like to thank you one more time because this was an impressive first presentation of your work. I'm very excited to see how it turns out. As for the team, I really appreciate you taking the time to join this session and learn about Milan's research. Next week, we're going to have Sai presenting her work on Ambly, the smart darknet spider for cyber threat intelligence. Thanks again to everyone who joined us, and we'll reconvene next week this time for our next seminar.
Yes, Professor?